In this first video, we are going to take a look at the differences between a strong acid versus a strong base titration curve with that of a weak acid versus strong base titration curve. The first characteristic of note is the starting point. You will notice that in the strong acid versus strong base titration curve, that the pH starts at a fairly low value. We contrast this with that of the weak acid versus a strong base. You will note that the pH value in the second titration curve starts slightly higher. The second characteristic that we want to examine is the titration curve as it approaches the equivalence point. You will note that in the strong acid versus strong base, the titration curve is fairly flat with a very gradual slope. If we contrast this with the weak acid versus a strong base, you will first of all note that there is a slight increase in the pH value, and then the slope is much more gradual in approach to the equivalence point. The third characteristic that we want to take a look at is the pH at equivalence point. If we take a look at the equivalence point of the strong acid versus strong base, you will see that it is at a pH equals to 7. If we contrast this for the weak acid versus strong base, you will note that the equivalence point is at a pH that is greater than 7. In the following videos, we are going to examine each of these characteristics. In this next video, we want to be able to take a look at how we are able to calculate the pH of the starting point. If we take a look at the strong acid versus the strong base, you will note that we are titrating 100 mils of a 0.1 molar HCl versus 0.1 molar of an NaOH. So the first calculation we do is the stoichiometric calculation. In this particular calculation, we are reacting HCl with NaOH to produce H2O plus NaCl. Now, when we do this calculation, what you will note is that we are going to be using a modified ice chart. So rather than using the ice chart from the equilibrium, what this will be is the initial, change, and in this case for the E, it will be the end. The values we use in here are the mole values. So if we take a look here at 100 mils of a 0.1 molar HCl solution, we are going to end up with a 0.01 mole of HCl. Because at the starting point we have not added any NaOH, the NaOH moles will be 0. And because there has been no reaction, the amount of water we produce is 0, and the amount of NaCl is 0. Now when we take a look, obviously no reaction is going to take place because there is no NaOH. So we go minus 0 moles, minus 0 moles, plus 0 moles, plus 0 moles. And we end up with 0.01 mole of HCl, 0 moles of NaOH, 0 of the H2O, and 0 of the NaCl. As you can see, we have a 0.1 mole of HCl. So in the second step, what we have to make a note of is that the HCl is actually a strong acid, and we learned that a strong acid completely dissociates 100%. So in the next equation that we take a look at, we have HCl that is remaining, completely dissociating into H plus Cl minus. Now when we take a look at this, we have to calculate the concentration. So if we take a look at the number of moles, we want to figure out the number of the concentration, so we divide it by the total volume. In this case, it's going to be 100 mils, or 0.100 liters. And this works out to be 0.1 moles per liter of HCl. Now, because it is 100% dissociation, we can then safely say that this is also going to be 0.1 moles per liter of H+. So when we find the pH, which is going to be negative log of 0.1, we now calculate a 1.00. And so as you can see on our titration curve, the pH starts at 1, and we are able to calculate a pH of 1 from the equation. In the next video, we're going to take a look at the pH of a weak acid versus strong base at the starting point. In this next part, we are going to take a look at the calculation of the initial point for the weak acid versus strong base titration curve. Once again, we take a look at the material that we're using, and it's a weak acid, and once again, it is a 0.1 molar CH3COOH or acetic acid solution, and we start off with 100 mils. Note that this is very similar to the one above in the strong acid versus strong base. Again, we are titrating this weak acid against a 0.1 molar NaOH solution. So in the first reaction, again, we look at the stoichiometric calculation. In this case over here, we are now reacting our weak acid, acetic acid, and we're combining it with the NaOH. What it will form is it will form H2O plus NaCH3COO. Again, we're going to use the modified ice chart. So I'm going to write end over here. And once again, we're going to calculate the moles. In the first point, the number of moles of CH3COOH is 100 mils of 0.1. So we end up with 0.01 moles. Because we added 0 amount of NaOH, we're going to have 0 moles. And because we have not formed any products, there's going to be 0 moles of water and 0 moles of sodium acetate. Because there's no NaOH formed or added, we're going to be subtracting by 0 moles. And then on the other side, we're adding 0 moles. And then in the end, we end up with 0.01 moles of CH3COOH. We have 0 moles of NaOH, 0 moles of H2O, and 0 moles of sodium acetate. Now, how this is going to contrast between the strong acid versus strong base and the weak acid versus strong base is the second step. Whereas a strong acid will dissociate completely and thereby have no equilibrium, we are now working with a weak acid, and in terms of the weak acid, there will be an equilibrium formed. Now, in terms of this equilibrium that is formed, the weak acid is going to be reacting with the water. And we draw a double arrow instead of a single arrow. And now we have the weak acid dissociating to form its conjugate base, and a hydronium ion is formed. Now, we are again going to use the ice chart, but in this case we are using the ice chart as was initially studied, which is in the form of the equilibrium. So we calculate the concentration of the acetic acid. So we take the moles of acetic acid divided by the volume, and so we get 0.1 molar. We don't worry about the water because it's not involved in the equilibrium. And initially there will be 0 amount of sodium or of acetate, and there will be 0 amount of hydronium ion. So we go and subtract, because according to Le Chatelier's principle, it's going to shift to the right. And you get 0.1 minus x, and x. So now we use the KEQ or the Ka equation to calculate the concentration of the hydronium ion. So we have Ka is equal to CH3COO minus times the hydronium ion concentration and that yields CH3COOH. So looking up the Ka, we get 1.8 times 10 to the minus 5 is equal to x squared all over 0.1 minus x. So if we compare the Ka value to the initial value, we see that the initial concentration value is significantly bigger than the Ka. Therefore, we can assume that this x over here is very small. Then this simplifies our calculation, and we end up with x is equal to 0.0013 molar, which is equal to the concentration of the hydronium ion concentration. When we take the negative log, we get 2.87. So as you can see, because of the partial dissociation, we end up with a pH value that is slightly higher than 1. So finally, if we take a look, we have 2.87, and if we contrast this to the initial, we have our 1.00. So as a result, if we examine this very first point, we now can see why the starting value of the strong acid strong base is lower than that of the weak acid strong base.